Let's flash back to some of the beginning chapters, the relationship between velocity, position, and acceleration. So I know that velocity is the change in position over the change in time, which is just basically a slope. So this is the slope of the position versus time graph. Acceleration is the change in velocity over the change in time, which is the slope of the velocity versus time graph. So if I have a position versus time graph that looks like this, then my velocity versus time graph, well, I know the slope is 0 there. The slope is 0 there. So when you have a curve and you're trying to find the slope, you're basically looking at a tangent line. So I'm looking at the slope of the tangent line there. I know the slope is positive to begin with. It goes to 0 and then becomes negative. So, and it looks like the slope is the steepest there. So it looks like it does sort of go down like that. I know I have to hit back to 0, and then my slope becomes positive, and it sort of evens out a little bit, and it looks something like that. My acceleration versus time graph would be the slope of this graph, and so that's 0 here. It's negative all along there. And slope looks the steepest at that point, so that looks like the most negative. And then here, the slope is the steepest somewhere around here. So something like that. That's a very crude sketch. This is stuff that we need to know in order to be able to deal with a harmonic motion. So let's take a look at some of the more specific examples that we will deal with. If I have x is equal to cosine of theta, let's go ahead and make it cosine of t. Then at 2 pi, this is my time graph, this is our time axis, and that's my position axis. The graph's going to look, I know it starts at 1, drops down to -1, and then comes back up to 1. So the graph, that's basically the cosine curve. It would just keep going on forever and ever, and going on forever and ever in the negative direction. My velocity graph, well, my slope is 0 here, my slope is 0 here, and my slope is 0 here. My slope is negative in between these two spots, and it's positive between these two spots. So that is so if that is my position graph, this is my velocity graph. This is the graph of my velocity would be negative sine of t, because the sine graph looks like that. That's the basic sine graph. If I took the slope of that, in other words, I found acceleration, well, my slope is negative here, or sorry, is 0 here, and it's 0 here. It is negative up until then. Here it's positive, being the steepest at that point right there. And then it's negative again. Wow, that looks a lot like that graph, except it's upside down. And matter of fact, my acceleration function would be negative cosine of t, where this is 2 pi here, this is 2 pi here. That's pi, 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 pi over 2, 3 pi over 2, pi over 2, 3 pi over 2, pi over 2, 3 pi over 2. And so if you kept going, basically there comes a cycle here. So if I start with cosine, I then go to negative sine, I then go to negative cosine. If I did it again, well, cosine creates negative sine, so negative cosine creates positive sine. Negative sine creates negative cosine, so sine creates cosine. Matter of fact, it just loops back and forth. So if this is position, this is velocity, this is acceleration, this is jerk, snap, crackle, pop, splat. Or if we started here, if that's position, then that's velocity, acceleration, jerk, snap, crackle, pop, splat. There are going to be some other variations here that, suppose instead of cosine of t, I had x is the cosine of 2t. What does that 2 do to the graph? Well, basically that means that I get back to where I started. If we think back to over here, I'm back to where I start at 2 pi. So when that equals 2 pi, I'm back to where I started. Here, when that equals 2 pi, I'm back to where I started. So if 2t equals 2 pi, then I'm back to where I started at pi. So my graph, if that's pi and 2 pi, my graph basically gets squished. It gets accordioned. So I'm traveling in essence twice as fast. So if that's my position. Now what does that do to the slope? Well, if I take any line, if I take a line like that, and then I push it into a smaller domain, it becomes steeper. And so what this is going to do is it's going to make my velocity graph steeper. So if that's 1 and -1, then for velocity, what that 2 does is it actually doubles the slope. And so this becomes 2 and -2 in my graph. Looks like that. And it keeps going on. And then, where that's pi. And then my acceleration, well, I basically not only made this steeper, but I've made it taller. So I've taken something like that, I squished it into a smaller space and stretched it out. And so this is even bigger. So this will go from 4 to -4. Where that's pi. So the number right here basically is a multiplier when it comes time to doing slopes. So we can make it more generic. If my position is cosine of omega t, then my velocity is omega, negative omega sine omega t. And my acceleration is negative omega squared cosine omega t. So every time I do a slope, I just multiply times whatever number's in front of t. Now, if I change the amplitude of this, so I now have x is equal to 5 cosine of 2t. Well, the 5 stays there. It's going to affect the slope. Definitely it's affecting the slope, but we still multiply by that. So the velocity becomes, well, 2 times 5, or 10 negative sine of 2t. And acceleration, well, multiply times 2 again, negative 20 cosine of 2t. And so this will become critical when we start talking about harmonic motion. One other aspect of it, if we think about, I have a circle here with an x and y axis, and I have an arrow here that is rotating around. If the arrow is spinning around at some constant angular speed, so if it has a constant angular speed as it rotates around, well, angular speed, the symbol for it is omega, which is the same symbol that we use for angular frequency. Well, angular speed and angular frequency have the same symbol omega. Well, angular speed has SI units of radians per second, and angular frequency has SI units of radians per second. So they look and smell alike, they taste alike. There's a philosophical difference between angular speed and angular frequency. But in terms of mathematical use, they can be done and used interchangeably. I've never run into a case in which the omega for angular speed and omega for angular frequency were not able to cancel each other out if they were, mathematically appropriate to cancel each other out. So angular frequency deals with the frequency of basically passing through radians, and angular speed deals with the number of radians you're passing by every second. That's the philosophical difference. So if there's a number up front here, which is omega, as I will reference later. So if this is x is equal to the amplitude times the cosine of omega t. If omega is bigger than 1, this means this arrow is spinning faster than normal. If it's less than 1, it's spinning not as fast as normal. But if omega is bigger than 1, it's spinning faster, which means that my speed here, this is not angular speed, but regular speed, my speed is basically increased. And that's what we're seeing mathematically here when I multiply by the number.